Okay, so we're looking at section 5.4 today. Remember in 5.3 we looked at sums and differences of angles within a trig function. Today we're looking at what if I have multiples of angles in a trig function? How do I deal with that? So you guys are going to have to, when I say know the identities, I basically mean be able to recognize them. So if you see a problem with a multiple angle, you want to know which formulas you have to use and be aware of what the formulas look like so that you can see when you have something that resembles them. But as far as knowing them to the T, you guys will have a formula sheet for these on a quiz or a test. Okay? We're going to be doing the same old stuff with these. We're going to be evaluating trig expressions, solving trig equations, improving trig identities. All right, so here's your double angle identities. If you're looking in your textbook, in section 5.4, they should be the first box of identities, right? Which page number is that?
471.
471. So that's where you're going to look when you're doing your homework, okay? Again, you don't need to memorize these. Just make sure that you can recognize them and know when to use them. All right, notice that for cosine, you have 3 different options. There is not a set way to say like, oh, you have to use this one or this one or this one for certain things. What are you looking for? You're looking for the one that's going to be the most efficient in your problem. So look at your problem, look where it needs to go, and try and decide which one of these is going to work the best for me. Okay? So keep in mind, these are when you have double angles. So if you have an angle times 2, then you'll use these to get them down to just the single angles. That's kind of what this goal is. All right, your power reducing identities. Notice that we have formulas for the sine squared, cosine squared, and tangent squared. They're your Pythagorean identities. But keep in mind that like when I replace the sine squared, I would replace it with 1 minus the cosine squared. So did I get rid of the power when I do the Pythagorean identity? No. So notice that what this does is if you ever want to get rid of the squared power completely, you can use these formulas, but you do pick up a double angle, so that's something to keep in mind. All right, and I believe that that is on the next page, so if you flip them, they're in the second green box in that section. That's where you'll look for those. All right, your half angle identities are when you have an angle divided by 2 and you want to get it into just a normal angle. Notice that you've got this plus and minus. All right, this is something that you guys have to pick depending on which quadrant your angle's in. So you'll have to look at the angle you're given, figure out which quadrant it's in, decide if that trig function is positive or negative in that quadrant, and then assign the sign. Notice that for the tangent, you have 3 different options. Again, you're just looking at your problem and trying to choose the one that best fits where you need to go. For the bottom 2, you do not need to pick a sign. So that's something that is nice about these if you're able to use them, is that they don't have to have, you don't have to choose the plus or the minus. They'll work out the way they're supposed to. Whereas this top one, you're going to have to choose a plus or a minus. All right, so those are all of the identities we're going to be working with today. Let's take a look at our first example. Okay, so we want to find the exact value without having to use a calculator. Notice that 195 is not an angle that I know. How can I rewrite this either as a doubled angle or a halved angle in order to evaluate this with one of the functions that we've just learned? Which angle would I write this as?
So we're not doing the like 180 plus 15. Would we be able to do that on a test? Or?
180 plus 15?
Yeah.
Well, you don't know 15 degrees.
180 plus 45 minus 30. Yeah.
Oh, good.
That's exactly
Okay, that's a big pain in the butt. On a test, if you could find 2 angles that add up to 195, you could use the addition. This one is actually easier.
I just want to make sure we...
Yeah, no, on a test you will be able to. On this section, they're going to make you use the multiple angles just to force you to like learn them and know them. But technically on a test, if I tell you to evaluate this, you can use any of the identities I tell you, or that you know. But let's say that I want you to use either a half angle or a double angle. What are you going to, how can you rewrite 195 either as 2 times something or something divided by 2? Which one's going to be the best? Huh? Something divided by 2, you're thinking? Okay, what's that something divided by 2 going to be? Whatever 195 doubled is, right? Which is 390. So 195 can be written as 390 divided by 2. Keep in mind the double angle, like had I tried to, don't write this, just watch. Had I tried to write the tangent of 2 times something, does 195 divide evenly by 2? So whatever angle is going to go here is not going to be one that I really know that well, right? So that's why we're not heading down that route. Okay, so plug this into your double angle. You get to pick now which tangent half angle, sorry I said double, I meant half, which tangent half angle is probably going to be the best for us in this case. You've got 3 options, right? So you've got the plus or the minus one, or you've got 2 ones that don't have the plus or the minus. Do you think you want to use the plus or the minus one? I wouldn't, just because then I have to figure out what quadrant it's in. It's really not that hard to do that anyway. Which quadrant is 195 in? Quadrant 3. What is the tangent in quadrant 3? Positive. So you know that if you did do that square root 1, you would be taking a positive value, right? That's how you use the plus or the minus, is you look at the original angle and you decide which quadrant it is and which sign it should be. Now, then I'd still have to square root stuff, so I'm still going to stick with one of the other ones. I'll just go ahead and use the 1 minus the cosine of x, which, what is my x value in this case? Look at your formula. You should have your textbooks out, open to the very first page of the section. 390. Yeah, so x is now the angle that you made divided by 2. That's what you're now using instead of the 195. That's all over the sine of 390. But notice, do we usually look at an angle that's over 360? We could rewrite it as the coterminal angle that's smaller, right? So which angle is coterminal with 390? 30 degrees, right? If you took off 360 from 390, you'd be left with 30. Now that's an angle that we know. Okay, so what is the cosine at 30 degrees? Square root of 3 over 2. What is the sine of 30 degrees? 1/2. So now on the numerator, I'm going to force this into a common fraction, so it'll be 2 minus root 3 divided by 2. But notice that this 1/2, I would end up multiplying it by 2 in order to take it off of the bottom. So if I multiply this whole fraction by 2, what happens? Those cancel, right? So again, just to walk through that, I rewrote the top fraction as 2 over 2 over root 3 over 2, so that's this part, and then I took my 1/2 and flipped it up as times 2. But now those 2's cancel. So this answer is just 2 minus the square root of 3. Are there any questions about how I did that? Yeah.
Are you allowed to just multiply something by 2?
Am I allowed to just what?
Like multiply something by 2, doesn't that change it?
I didn't just multiply by 2. I took this 1/2, dividing by 1/2 is the same as multiplying by 2. So I took that off the bottom and moved it up.
Okay, that makes sense.
Yes.
Like, why is there still 2?
Yeah.
Where? This one?
Yeah.
That's coming from this top, combining it into one fraction. 2 over 2 minus root 3 over 2. That's all in the parentheses. I condensed that into one fraction. Then this 1/2 down here is that 2. Okay. I just did some algebra steps in there. That's all that is. One more time. Ready? This part right here, this stuff, all of that is what was already in the parentheses up here. All I did was condense that into one fraction. This 1/2, rather than dividing by 1/2, I multiplied by 2. Do we all see that now? That was just some algebra simplification. You might have done that in a few more steps than what I did. Are we ready for the next example? Okay, this is the one where you really need to just bear with me. This is going to be a long one. Okay. They want you to write the expression as one involving only the sine and the cosine of theta. That means that what we need to do is break this down so it does not have the 2 theta or the 5 theta. Now, in the last section, we were taking this 2 theta and we would have broken it into the sine of theta plus theta, and then we would have used our sum expansion. But that sum expansion condenses into the formula that you guys now have for the sine of 2 theta. That's where that formula that you have now came from, was just from doing that expansion and simplifying it. So we now get to use that simplified version every time. Okay? Just to demonstrate that, so don't write this down, but just watch for a second. Last section, you guys would have taken this part and you would have said that this was the sine of theta plus theta. You would have expanded that to be the sine of theta times the cosine of theta plus the sine of theta times the cosine of theta. That's your addition expansion. But those are the same, so it would have been 2 sine of theta cosine of theta. Look at your double angle identity for the sine of 2 theta. In your book, what is it? It's this thing. So basically, we're just eliminating this work. Do you see that? Okay? So you now get to just use those formulas where you can to eliminate a few steps of work. You take advantage of that. My last class really wanted to keep on doing that expansion because it was something they got comfortable with in the last section, but it gives you 2 or 3 more steps. So use the double angles where you can. All right? So here I can just expand this into the formula that I just talked through. So I can just straight up rewrite that first term as 2, sorry, my wrist is getting in the way. So as 2 sine of theta cosine of theta. I get to just write that. All right? Plus, now what do you guys want to do with the cosine of 5 theta? I have not given you a formula for 5 theta. What can I do? There's a couple of different things. Think of the most efficient thing you can possibly do. No. The side conversations really need to stop up here, please. Okay. First of all, you have a double angle identity. Do you have a triple angle identity? No. So when you have an odd angle, you really need to break that into an even angle, and then the only odd angle that you want is a single theta, right? You don't have anything for 3 theta. You don't have anything for 5 theta. So what I would do is rewrite this as the cosine of 4 theta plus theta. You are going to have to do one addition expansion here. What that's going to do is allow my next step to break into 4 theta, but I'll be able to use a double angle on that. So watch this. This first part, I'm not going to have to do anything else with this because it's already in terms of just theta, right? So I'm just going to keep on bringing that down. Now I have to expand my cosine out. So if you go back to your cosine expansions, this is the cosine of 4 theta times the cosine of theta minus the sine of 4 theta times the cosine, or I'm sorry, not the cosine, times the sine of theta. So what you have now, the only things that you have left that still are not in terms of just theta are this term and this term, right? So a lot of you are going to be tempted to write that as 2 theta plus 2 theta and then use your addition expansion. There is a better way, and here it is. Rather than doing that, you can still use your double angle. So you can do 2 sine of theta times the cosine of theta plus, you want to look at this as being the cosine of 2 times 2 theta. So this is now a double angle, you can see, where, if you're looking at the formula, I believe they tell you cosine of 2u equals blah, 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 right? Your u is just 2 theta. So we're going to be able to put it in terms of a double angle, and then, again, we'll have to apply another double angle formula. Does everyone see how this is still a double angle? Yeah?
It's just longer but not wrong if you split it up into 2 theta plus 2 theta, right?
Right. It's just going to create a really long string of work that you're probably not going to fit on one line of page, and it's going to create more steps.
Okay.
So I would try and do this. Okay, so keep on writing. You've got the cosine of theta. We're going to do the same thing to that sine of 4 theta. We're going to look at this as the sine of 2 times 2 theta times the sine of theta. All right, so let's expand those double angles out. We've got 2 sine of theta times the cosine of theta plus, and here's where I have to apply the double angle on this thing, right? So for the cosine, we kind of get to have a choice of which one we want to use, right? You have 3 different options. Yeah? It really doesn't matter which one you do. I'll just use the first one for the sake of picking one. All right, so I'm going to use the cosine squared of theta minus the sine squared of theta, or 2 theta, I guess. So what we have to do is do the cosine squared of 2 theta. Do we all see why that has to be a 2 theta? Because we can only break down doubles at a time. So I can go from 4 and cut that down to a 2 theta. And then on the next step, I'll be able to go from 2 theta down to just theta. Okay, that is, and I should put this in parentheses, minus the sine squared of 2 theta. And actually, I didn't really choose the most efficient one here. Why didn't I choose the most efficient? How many double angles am I going to have to use now here on the next step? I've created a situation where I'm going to have to plug in a formula here and here. Take a look at your cosine double angles. Is there a different one I could have used to avoid having to do this twice? Yeah? So I'm going to backtrack on this and say instead of using that one where I'd have to plug it in twice, we can use either of the other 2. So if we use 2 cosine squared of theta minus 1 or 1 minus 2 sine squared of theta, we're only going to have to plug in one double angle. I don't think it really matters which one we do, so I'm just going to use this one. Again, it's just for a matter of picking. So now all I have to do is plug in a double angle on 1 on the next step rather than 2 steps, right? That is all still times the cosine of theta minus, for the sine, we didn't really have a choice. We were told that this has to be for this double angle. We only have one formula. It's going to be minus 2 times the sine of 2 theta times the cosine of 2 theta times the sine of theta at the very end. So here's what we just plugged in. All right, so now I have a couple more places that I have to simplify things down. I need to break each of these guys down separately. And we're going to have to break this guy down. Something I want to point out is that it might be easier to look at this step. Instead of putting the squared in this spot that we usually do, it might be easier for me to put the 2 sine of theta thing and square that. Oh, that got a little messy. Let me try and clean that up a little bit so you guys can see what I'm doing. All right, so what I'm saying is to square, look at the squared like that. It means the same thing, right? It doesn't matter if I put the squared here. It means to take the whole trig function and square it. So that's an okay move, and it will make this next step actually easier for us to see. And you'll see why. All right, so keep on going. We've got 2 sine of theta, cosine of theta, plus 1, oops, and I should keep this in parentheses, so plus 1 minus 2 times the quantity. I have to put in my double angle formula for the sine of 2 theta, which is 2 times the sine of theta cosine of theta. That's squared. And then all of that stuff is times the cosine of theta. All right, minus, I've got 2 times, I need to apply my double angle to this sine of 2 theta right here, which is going to be 2 sine of theta cosine of theta. Okay, and then I need to apply a double angle to this cosine of 2 theta. Which one do you guys want to use? And it just make a choice, right? Does it matter this time if I use that cosine squared minus sine squared? Am I going to be picking up a double angle in this again? No. So this time I don't really have to worry about putting in 2 of those because I don't have to break it down anymore. So I could at this point use that cosine squared of theta minus the sine squared of theta. And then all of that is still times this last sine of theta. All right, the good news is that do you have any more double angles that you have to expand out? So at this point, we just need to start condensing and things like that. So you've got it all expanded out. Okay, so let's start looking at how can I start simplifying this, just one thing at a time. So again, that very first part, we don't have to do anything to this. So we've got 2 sine of theta times the cosine of theta. Now on this part, we need to take this squared, and we need to square this 2, and we need to square this sine, and we need to square this cosine, right? So what is that going to look like? Plus 1 minus 2. Now everything inside of the parentheses is getting squared. So that's going to be 4 sine squared of theta cosine squared of theta. And all of that is still multiplied by the cosine of theta minus, now here I'm going to start kind of trying to rearrange some stuff. So first of all, I'm going to multiply this 2 in. Notice that anything that's just multiplication without any addition in between, you can just kind of write as one big string, right? So I could write 2 times 2 sine of theta cosine of theta. I'm going to bring, just because this is something that's hanging out on the end and it's kind of awkward, I'm going to bring this guy and multiply it in between. So I'm going to now tack that in right here and see what that does, times the cosine squared of theta minus the sine squared of theta. Okay, back to the beginning, see what we can keep on doing. We've got 2 sine of theta cosine of theta plus, this can now be condensed down into 1 minus 8 sine squared of theta cosine squared of theta. That all times the cosine of theta minus, now all of this stuff here that's just multiplied can kind of get multiplied together. So this will be 4 goes together. These 2 sines can multiply to be sine squared. I've got a cosine hanging out. And then on the next step, I'll distribute all of that through to my cosine squared of theta minus the sine squared of theta. All right. So on this next round, I'm going to take this cosine in and distribute. So I'll have plus the cosine of theta minus 8 sine squared of theta cosine squared of theta. And actually that should be cosine cubed because I put that other cosine in, so cubed of theta, minus 4 sine of theta cosine of theta, or cosine squared of theta cosine of theta. That's going to distribute, that whole big piece is going to distribute into both of these terms. So that is going to be 4 sine squared of theta cosine cubed of theta. And then minus or plus 4 sine to the 4th of theta cosine of theta. All right, everything is now all expanded out. What do you guys see that we can still do? Condensing at least, right? So you guys still have this 2 sine of theta cosine of theta. Is there anything that I can condense with that one? No? So I'm actually going to write, I'm going to kind of start reordering this. I'm going to write just the single term first, so the cosine of theta term. Then I'm going to put my single terms, so the 2 sine of theta cosine of theta. Next I'm going to try and put the next highest powers, which is going to be combining these two together. Did I hit that right? Yeah, so the sine squared cosine cubed terms I'll put next, which are going to be minus 12 sine squared of theta cosine cubed of theta. And then we've got plus 4 sine to the 4th of theta cosine of theta. You could, if you really, really wanted to, on these last 3 terms, you could take out a 2 sine cosine and then group that. But I wouldn't think that that would make it look all that much better. So that is about as condensed as we're going to get, where all of our angles are single thetas. Any questions on that? Tedious work, right? Lots and lots of tedious work.
Wait, that's the finest thing though.
Yeah, like I said, you could, if you really wanted to, on this last step, take out a sine cosine from each of these, but really all they asked for was just to write it as an expression in terms of sine of theta and cosine of theta, right? And this is that, and it's condensed as much as it's all multiplied out. Does anyone have any questions on that? Okay, that is the most tedious problem we have to do. But we're not done. Okay, so we've got some proving the identities. We've got a couple of these, and then we've got a couple of solve the equations, all right? For this one, remember this one kind of goes against the rule of start on the most complicated side. Why do I think I want to start on this side? Because it has a 4x. Remember, it's easier to expand out a multiple angle than it's going to be to try and get the correct formulas to condense it down on the other side. It's going to be really tricky to do that on the right-hand side. So it's actually easier to expand a multiple angle out. All right? So let's start on that one. Based on what I told you guys, how can you avoid having to do a couple of steps? Rather than doing the sine of 2x plus 2x, you can look at that as being the sine of 2, instead of 2x plus 2x, you would do 2 times 2x. Yep, so that you have a double angle. Then we apply our double angle formula. For the sine, you only have one option. What is your formula for this? What will you get? 2 sine of 2x, good, times the cosine of 2x. Yep. All right, so I have to apply double angle here and here. So for that first 2 sine of 2x, it's going to be same formula except for now I can knock it down to x's. So 2 sine of x cosine of x. Now the question is for the cosine of 2x, you have 3 formulas. What you need to keep in mind is what are you trying to make this look like? And I also forgot this 2 right here technically wasn't a part of what I just did, right? So that is still on the front. Do you guys see that? So I have that 2 is this. This 2 is part of the expansion on that. Notice what is this going to multiply to? 4 sine of x cosine of x. Oh, hey, look at that. So now when you're choosing which formula to use here, do you have a formula that matches this? You do. So that would be the one that you'd want to choose here because you want to make it match, right? So here we would just say, well, I may as well use the cosine double angle that gets me where I want to go. 2 cosine squared of x minus 1. And then your last step is simply just to multiply those two 2's together to get the 4 sine of x cosine of x times 2 cosine of x squared minus 1. And now we have the pieces that match. So much easier than the last one, right? All right, are there any questions on that and why we needed to start on the left-hand side? All right, let's look at another one. All right, notice that you have multiple angles on both sides now. You have to be careful about which one do you think is going to be easier. Ask yourself this, is it easier to expand to a bigger multiple angle or take a bigger angle, multiple angle and condense it down? What? So which one are you talking about? So like, do you mean expand 2x or 4x? Like, will it be easier to make this 4x match this 2x, or will it be easier to make this 2x match this 4x? When you say 2, I don't know. So do you want me to start on this side, or do you want me to start on the left side? Well, again, if you start on this side, you are going to have to somehow get a 4x, right, in an angle. How are you going to expand that out to be a 4x? Do you see what I'm saying? You guys are not giving me much feedback right now. Do you see what I'm saying about how it's harder to take a smaller angle and make it bigger than it is to take a bigger angle and make it smaller? Okay, so which side do I start on? The right side. Thank you. Yeah, it will be easier for me to work on this. All right, so first of all, do you think I need to break this angle down? Do you have any x's over here? Just regular old x's? So I probably don't want to make regular old x's, right? That would be pointless. So I'm going to leave this alone. I'm only going to break down this 4x. So let's start. Like I said, I'm just going to recopy down that 1/2 sine of 2x. I decided I didn't need to do anything with that. Whoops, sorry about that. Over here, I'm going to look at this 1 minus the cosine of 4x as 1 minus the cosine of, what do you think? 2 times 2x. And then I'm going to use a double angle formula on that. Take a look at where you're trying to get to. You have 3 different cosine double angles. Which one do you think is going to help me match what I want to get to? Look at what you're trying to get to. only have sines going on here. So you should probably choose the one that doesn't have any cosines, right? Which would be?
1 minus 2 sine squared of u.
Thank you. 1 minus 2 sine squared of, and what is your u? 2x. Notice that I put parentheses around that because distributing that negative in is going to be important. All right. So I have 1/2 of the sine of 2x times, when I distribute that negative through, I get 1 minus 1 plus 2 sine squared of 2x. What happens? The 1's are going to cancel. And when I multiply all this through, so you have right now 1/2 times the sine of 2x times, and you have that times 2 sine squared of 2x. So what happens? The 1/2 and the 2 cancel, and then when you condense these, because they have the same angle, you can condense them. They become, multiply them together, sine cubed of 2x. And hey, that's what we wanted. All right. Are there any questions on that one? All right, on to the solving. We've got 3 of these. This one, there are multiple ways that you can do this one. Some ways easier than others. It's true. All right, where do you think you should start looking, first of all? What formulas do you think you should have in mind right now? Half angle. I would be looking at my half angles. Which half angles would you be looking at? How many different options do you have? 3. I have 3 different options for the tangent of a half angle. Which one do you think we should work with? Okay, you guys are all saying the top one. How are we going to use the top one? And you can get there any way you do this, you guys. You will, like, you could use any of the other 2 as well. Let me ask you this. Are you going to plug in, like, the square root thing over here? Or what could you replace this side with based on what you see for the half angle? What is this technically in terms of that thing? What's the only thing you're missing? So if you wanted to lose the square root on something, you would square both sides, right? So this could be replaced with yes. That could be replaced with tangent squared of x over 2. Now, why did I decide that this was going to be nicer than plugging in a square root stuff over here? Because if I plugged in a square root thing over here, what would be your very first step to solving this? You would have to square both sides, and then when you square this side, you would have to FOIL it all out. Also, when you square both sides, you have to check for extraneous solutions. Because when you square both sides, you open up the solution that, like, 1 could equal a negative 1. Is that true? No, but you're going to get those solutions where one side would be a 1 and one side would be a negative 1 because you've squared it to both be positive. In the original problem, that might not be the case. So this is why I have chosen to go down this path, is because if I replace this side, even though it seems like the more obvious thing to do at first, it's going to create a buttload of work. This is going to save me. How do I go about solving this? Remember, when we're solving equations, we want one side to equal, typically if we can, right? We want one side to equal 0 so that I can get factors of some sort, right? Sure. So 0 equals, I'm going to move it over to this side so that I keep a positive squared term. Now what can I do? Pull out a tangent. Yep. So at this point I can say, well, this is the tangent of x over 2 times the quantity tangent of x over 2 minus 1. Now what can I do? Set them both equal to 0. So from this I'm going to get that the tangent of x over 2 could equal 0. From this I'm going to get that the tangent of x over 2 could equal what? 1. Okay, we have not yet solved where I've had a double angle or whatever in here. You save worrying about this angle until the very end. So still go about this the same way you used to. So what you want to do is say x over 2 could equal, and then basically what you're answering is the tangent inverse of 0. So you're saying where could the tangent be 0? Where could it be 0? What? Okay, tangent of 0. Tangent is sine over cosine. Sine is your y value, so you're looking for when is your y value 0. 0 and pi, right? That's where your y value is 0. You guys are saying pi over 4. At pi over 4, your tangent is 1. So from this solution, we get 0 and pi. Here is where you deal with the half now. So at this point, now you take whatever solutions you found and you multiply it by 2. Okay, something that I need to tell you though is that anytime you have this situation where you have a half angle or a multiple angle, you need to take into consideration that we could have all of these solutions plus 2 pi k. Even though I'm telling you that I only want this interval, you'll see why in just a little bit, okay? This will change things. So what you guys want to do is put this in terms of infinite solutions, and at the very end, plug in k values and see which ones actually get you in that interval. Okay, so when I multiply by 2, I get x could equal still 0 or 2 pi plus full revolutions plus 4 pi k, right? Because I have to multiply everything by 2. All of it in order to cancel it. Which of these solutions are within my intervals? Is 2 pi really in that interval? No, because I've put a parenthesis. If I add 4 pi k onto 2 pi, of course I'm going to be outside of that interval as well, right? Okay, this is going to come more into play up here. So let's start working on this side now. What we're looking at is when does x over 2, or when does the tangent equal 1? So tell me, when does the tangent equal 1? And? Five pi over 4, yes, because we want to be in quadrant 3 so that we get 2 negatives make a positive 1, right? Plus we have to add on 2 pi k onto each of those. So I'm kind of writing this as though this 2 pi k is being applied to the pi over 4 and the 5 pi over 4. Multiply that all by 2. All right, this gives you that x could equal pi over 2, once I multiply that by 2, and 5 pi over 2 plus 4 pi k. Does everyone see what I'm doing here? Oops, I don't need that parenthesis. All right, the easier way to look at this solution is going to be to write these as one big fraction. So I know I'm kind of put myself in a little corner here. What I'm going to do is draw an arrow, and it's going to go way far away from here. So I'm going to take this all the way up to here. All right. What this gives me, you guys, is x could equal, now if I take pi over 2, and I want to add on plus 4 pi k, but I want to write this as one fraction, that's going to look like pi plus 8 pi k over 2, right? So what I need to do is look at this and see, when I plug in integer k's, which values still keep me in between 0 and 2 pi. All right? So first of all, if I plug in k as 0, then this goes away and I get pi over 2. Is that still good? Okay. If I plug in k as 1, whoopsie, hold on. If I plug in k as 1, then I get pi plus 8 pi k, which is going to be 9 pi over 2. Is that still within 2 pi? No, 9 pi over 2 is way outside. So that's actually the only solution I'm going to get from this part. Okay, then I have to do the other thing for same thing for 5 pi k. So I get 5 pi plus, and it's going to be another 8 pi k when I put it into the same denominator. Plug in k as 0, that means that this doesn't exist. So it's 5 pi over 2. Is that within my interval? No, it is not. So I get nothing from that one. Do you guys see that? All right, so my solutions for this are what? Overall. Yep, I had x could equal 0 and pi over 2, and that was it. Are there any questions on that? Yes?
For the tangent of x over 2 equals 0, when you do x equals 0 for 2 pi plus 4 pi k,
Yeah.
does 0 have the
Plus 4 pi k, yes. It's just that if I added 4 pi k onto that, I'd be way outside of my 2 pi interval.
So you just automatically know that.
Yeah, so that one was kind of obvious that adding 4 pi k was outside of it. But you still want to put it to check it and be aware of it. Okay, the next one. All right. You have a sine and a cosine. Is that good for you? No, it is not. But what do you notice? What do you notice about your angle values? Huh? What? What do you notice about the relationship between 3x and 6x? One is double the other. And hey, we've got double angle formulas. And in fact, we have double angle formulas that could be rewritten then in terms of sine, perhaps. So let's take a look at that. What I want to do is say this is, oops, I don't want to be in red yet. I want to say I've got the sine of 3x equals, and I'm going to rewrite this cosine as being the cosine of 2 times 3x. And I'm going to apply double angle with the 3x. Now you have 3 different cosine double angle formulas. Which one are you going to use here? Which one will work to your benefit? Remember, you need to solve this, so you need it all to be in terms of some similar thing. Yep, I would use that last one that is in terms of strictly sine. So 1 minus 2 sine squared of 3x. Now what? I've got it all in terms of sine. What should I try and make this look like? Something that I could... Yep. So I'm going to add my 2 sine squared of 3x over. I am going to keep plus the sine of 3x and then minus 1 to get my 0. You can only factor things if they not only have the same trig function, but also they have to have the same angle value. So like if this was a 3x and this was a 6x, I would not be able to factor that. Okay? But these match, so I'm good to go. So this is going to be 2 sine of 3x in one group. In my other group, I'm going to have just sine of 3x. I know that I need to multiply to 1, so I need 2 1s. I need to have a positive 1 sine of 3x in the middle. So I'm going to put the positive on my multiplication with the 2 right here and the minus here. Now that I have factors, I can set them each equal to 0. You can see from this factor that I'm going to get to the sine of 3x equals 1/2. From this guy, I'm going to get the sine of 3x equals -1. Again, don't do anything with that angle in the middle until the very end. Those should not create that many problems for you. All right, so when does the sine equal 1/2? Where? Yes, at pi over 6. And 5 pi over 6. And actually, I'm trying to think about where I want to write this. So actually, pi over 6. And also, I'm going to add, what should I be adding on right now? Plus 2 pi k for all of these problems, right? And then I'm going to say, and 5 pi over 6 plus 2 pi k. Okay. How can I rewrite each of those so that I have x equals and also so that I have common denominators? I'm going to try and do that all in one step. So let's do this. Ready? I'm going to take all of that. So I'm going to have 3x equals, I want you to condense this down into a common denominator. So that's going to be in the numerator, pi plus 12 pi k over 6, right? And then I'm also going to have 3x equals 5 pi plus 12 pi k over 6. So now here's kind of the last step that I was going to try and do in one, but I'll just erase and let you guys see it now. If I want to divide by the 3 so that I can get x alone, so if I want to get 3 off of this side, what's going to happen? My denominator over here is going to change to be 18 because I'm dividing by 3 on both sides, right? So like here, when I take my 3 and divide it, it's going to become 18. All right. I'll look at those in just a little bit. Let's get over here and see what's happening with my sine of 3x equals -1. So when does the sine equal -1? Remember, sine is your y value. 3 pi over 2, right? And then we have to plus 2 pi k. Keep in mind you always have to do that plus 2 pi k when you have a multiple or a half angle just to see what happens, okay? So any problem you do with a multiple angle, you have to act as though you're giving me all solutions and then at the very end go back and see which ones actually fit. All right. I need this to be in terms of x, so to kind of go through the same work. 3x equals, if I combine this into one fraction, this would be 3 pi plus 4 pi k over 2, but I want to erase the 3 off of this side, so my denominator becomes 6. All right, so now I'm ready to go through my possible solutions. What I need to do is plug in k values and see which ones are in between negative pi and positive pi. All right, so let's come down here to this guy and see what solutions I get off of this guy. First of all, I should plug in k is 0, right? So when I plug in k as 0, is pi over 18 in that interval? Yes, so that will be one of my first solutions, is pi over 18. Okay, plug in k as 1 down on this guy. If I plug in k as 1, then I get 13 pi over k over 18. Does that fit in the interval? 13 pi over 18 is, in fact, still less than a full pi, right? Because your numerator is less than your denominator. Also notice that I can plug in a negative 1. So hold on. I've got 13 pi over 18. I can plug in a negative 1 as well, right? And I'll have pi minus 12 pi, which will be negative 11 pi over 18. Is that in the interval? Yes, because I'm going from, instead of 0 to 2 pi, I'm trying to go negative pi to pi. Okay, so basically from these values, you're adding 12 pi or subtracting 12 pi to see how long you can go. So if I had 2 for k, I'd have 24 pi plus pi would be 25 pi over 18. Is that outside of my interval now? Likewise, if I took my negative 11 and subtracted another 12 pi, I'd be at negative 23 pi. Is that outside of my interval? Yes, so I'm done with that set. Now look down here. If I plug in k as 0, I get 5 pi over 18. That's in my interval. And I'm adding or subtracting, again, multiples of 12 pi into the numerator. That's what you're doing here, is adding or subtracting multiples of 12 pi. So when I add 12, what does it take me to, onto the top? How much? Is that in my interval? Yes, that is still less than a full pi. Can I keep on adding 12s, or am I done going that way? So now I have to start on the 5 and subtract 12. When I subtract 12, it takes me to, is that in my interval? If I subtracted another 12, would I be in my interval? No, because it would take me to negative 19, and that will now be greater than 1. So now I am done with all of my solutions here. You would not get all of these if you didn't do this plus 2 pi k. If you forgot to do this, you would only get pi over 18 and 5 pi over 18. Do you see what I mean? You would miss all of those other ones that you end up getting. So that's why it's really important that you add those 2 pi k's on. All right, come over here. K is 0, so you get 3 pi over 6 or pi over 2. That's definitely in your interval. Now I'm not adding or subtracting 12 pi, I'm adding or subtracting 4 pi. So if I add 4 pi over 2, I'm going to have, so 4 pi added onto that is going to be 5 pi over 2. Is that outside of my interval? Yes. If I subtract 4 pi, I'm at negative 3 pi over 2. Is that outside of my interval? Yes. Negative 3 pi over 2 is bigger than negative pi in the negative direction. Right? You cannot have, in this interval, you cannot have a numerator bigger than the denominator. Okay, so that's all your solutions. Are there any questions on that one? And what our main thing here is, do you have any questions on why we have to add on these 2 pi k's and how to check to make sure you've got all of your possibilities?
Why would it -1?
Negative 1 for what? For this one? So if you plug in, oh, wait, you might be right. I did my math wrong. Did I? Oh, because I was looking up at pi over 2. I'm sorry. You might be right. So if I did 3 pi minus 4 pi, I'd have negative pi over 6. And that is in the interval. Thank you, Mimi. So negative pi over 6. Good. Could I subtract another 4 pi? Because I would have, maybe, because I would have 3 minus 8, which would be negative 5 pi over 6. Is that still okay?
Yes.
Yep. Sorry. I was looking up at the pi over 2 and forgot that I had a denominator of 6. Thank you. Yep. So all of those would also work. All right, last problem. Find all solutions in the interval 0 to 2 pi. What do you notice? It looks kind of similar to what we just did, but why is this one worse? What?
Yeah.
It's got an odd in there, which it'd be fine to have an odd if I had like 5x and 10x, because then they would be double or half each other. The problem here is that neither of them are double or half, right? So the book goes about this in a way that I find extraordinarily tricky. What the book will do, just in case you decide to go back and look, is they will break this all down into just single x's. And it turns out to be it turns into something that's like 4 sine cubed of x minus 2 sine squared of x plus 3 sine of x plus 1, which does not fit the grouping factoring technique. And then they expect you to factor that, and I'm not sure how in the world they were expecting you to factor that. Yes? Go ahead. So I have come up with a different solution that does not apply double or half angles and is 1,000 times shorter and less confusing. You ready? Okay. What I do, and you could technically, you guys, apply this technique that I'm about to show you to the last problem I did. If you understand it well enough, you can do it as well for the last problem. So I'm kind of giving you a couple different ways. This is the technique you're going to have to use if you don't have double angles. If you have double angles, you can really use whichever one makes more sense to you. Okay? Okay. So here, what I'm going to do is instead of trying to break these down to be matching angles, I'm just going to say, whatever, that's too tricky. I'm going to deal with the fact that I've got a sine and a cosine. I'm going to set my sine of 4x, and I'm going to move over my cosine of 5x. So for this technique, you're noticing that these two functions are cofunctions of each other, right? I can write one in terms of the other using that pi over 2 minus the angle. So what I'm going to do is say, well, I can technically rewrite this in terms of the sine by doing this, by saying that the sine of 4x equals, I'm going to change it to the sine and write it as pi over 2 minus 5x. Do you all agree with that? Okay. So now you have to kind of use some logic. What we're saying is that I have two sine values of two angles that are going to be equal. So you have to think through what are the only times that sines would have the same value. When will the sine values have, what would the relationship between the angles have to be in order for them to come out to have the same exact sine value? What's the easiest? Is if the angles are the same. That would be the easiest scenario, is if you had that the angle 4x was exactly equal to the angle pi over 2 minus 5x. Agreed? What's the next easiest scenario? Is if one angle is equal to the other plus a full, plus any revolution, right? So I could say that, well, if I just add any revolution of 2 pi k, this angle will technically come back around to this stuff right here, right? And it should be the exact same sine value. So I'm taking that angle and saying I can add any number of revolutions. They should have the same sine value. This is your easiest version. This next version you have to think about a little bit, and so I'm going to kind of draw really quickly a little sketch to help you through it. All right, let's say that I give you, this is your angle, let's say. So let's say that this is 4x. Which other angle would have this same sine value without having it be a revolution that comes right back? So this first version is us saying that any other angle that comes back to this revolution would work. Which other angle in here would have the same sine value exactly? What? down here. Sine is which value? The y value. So you want it to have the same y value, which would be which quadrant? Over here, right? So how could you write this angle? You could write it as, and we're also assuming, yeah, so basically you take pi minus the angle, right? Do you see what I'm saying? So this would be, and I shouldn't use that 4x maybe because it's going to make things a little bit icky. I'm just going to use a general theta. Like if this is theta, then this angle all the way around is going to be pi minus theta. That's the only other time where the signs are going to be equal, plus any revolution of that, right? So how do we write that? We say that 4x could equal pi minus our angle right? Plus any 2 pi revolution of that would work. Does anyone have any questions about what that pi minus business is all about and why that also works? Make sure you ask a question now. Do you all get it? Yay. Okay. So now we have to solve these. All right. Let's start on the first one. So over here, we would be adding our 5x over to get 9x equals pi over 2 plus 2 pi k. That gives me 9x equals, I'm going to condense this just kind of like the same work we were doing before. If I condense this into one fraction, it's going to be pi plus 4 pi k over 2. And then to get x alone, over what? Yep. Over 18. Okay, I'm going to leave that for a second and do the same thing with my other guy. Notice that here we've got, so I'm going to kind of rewrite it out for a second. I have to distribute that negative sign through because that does kind of change things a little bit. Okay. All right. So now instead of adding 5 pi or 5x, I'm going to subtract it. So now I don't get a 9 on the other side, I get a negative x. I'm also going to combine these two guys, which will give me pi over 2. Because pi minus a half a pi leaves me with a half a pi. And then plus 2 pi k. Okay, now here's where you have to be a little bit tricky about this. I have to make this pi over 2 negative, right? And you can subtract 2 pi k, right? So you can take the negative into both. Does it really matter which sign it is on the 2 pi k part? Like whether I add a full revolution or subtract a full revolution, does that really matter? No, so I just like to keep that a plus always. You don't have to. You can leave it as subtraction, but I just kind of like to have it as a plus. You do need the negative to go at least on this part though. The only reason why I get to keep that a plus is because it really doesn't matter because k could be a plus or a minus, so it's going to end up being all the same anyway. All right, let's get it all together in one fraction. X equals negative pi plus 4 pi k over 2. So now what I have to do is look at each of these and see which k values are going to give me values in this interval. Notice I'm going from 0 to 2 pi. Okay, so think about that. If I can go from 0 to 2 pi, what can my numerator go up to in order for it to cancel down to 2 pi? 36 positive, right, is the biggest that I can get. What's the biggest that my numerator can get up to here? 4, so keep that in mind. So over here I'm going to add on k's. I'm going to be adding on 4 pi's until I reach over 36, right? All right. So I can have the solutions. X equals First things first, plug in a 0 for k here, and I get pi over 18. Notice, am I going to do negative k's this time at all? No, because I don't need negative values. I'm in between 0 and 2 pi. So I'm just going to add 4 pi's on, right? So if I add 4 pi, I get 5 pi over 18. That's okay. If I add another 4 pi, I get 9 pi over 18, but that simplifies to, okay? So I was at 9 pi over 18. If I add on another 4, I get to 13 pi over 18. If I add another, 17 pi over 18. So I'm going to have quite a bit here, aren't I? Okay, plus another 21 pi over 18. Could I simplify that one? They both divide by 3. So if I divide 21 by 3, I have 7 pi. If I divide 18 by 3, okay? What was I at? 21. So the next one is 25 pi over 18. 29 pi over 18. These are all solutions you would miss if you didn't do the 2 pi k business, right? All right, plus, so I'm up to 33, but 33 and 18 both divide by 3, so it's going to be 11 pi over 6. Can I do one more? I was at 33, right? If I add 4 into 33, I get 37, which is over 36. So I stop there. That's all of the solutions I'm going to get here. Now I have to look over here. Notice that since my denominator is smaller, it's actually going to go faster. So first of all, if I plug in 0, I get negative pi over 2, but that's not in my interval, right? So I need to add a 4 pi. That's going to take me to 3 pi over 2. Is that in my interval? If I add another 4 pi over 2, I'm going to get to 7 pi over 2, but that is too much, so we are done with that. All right, guys. Here is your homework. Come on. I know this is exactly what you were wanting to do all weekend. All right. You've got, guys, listen, it's really not that many problems, right? Remember, the later ones are usually the multiple choices or true falses. So you really only have a handful of ones that you have to really solve. Yes, they're going to be long though, okay? So be ready for the fact that yes, they're going to be long, tedious problems. That's why I gave you fewer of them. The ones I gave you? Yep. So I gave you guys, I think, everything that you really need for the homework. You might have to do a little tiny twist, but I've given you kind of like the big old concepts.